Hello students, in this session we are going to deal with Zeroth law of thermodynamics. Last section I was discussing about two types of walls which separates system and the surroundings. The first wall is called adiabatic wall, which is insulating wall, so there is no heat transfer between the system and the surroundings. The second wall is called diathermic wall, which is a conducting wall. So there is a transfer of system between the there is a transfer of energy between the system and the surroundings. So zeroth law based on those two things. Here system A and system B are separated by adiabatic wall. System A and system B are separated by adiabatic wall, so there is no exchange of heat between A and B. System C is separated using a diathermic wall. This line is diathermic wall. So there is a transfer of heat between A and C, and there is a transfer of heat between B and C. Okay? C is separated from A and B using a diathermic wall. So there is a transfer of heat between A and C, and also there is a transfer of heat between B and C. But there is no transfer of heat between A and B directly, since they are separated by adiabatic walls. Now zeroth law tells that if A and C are in thermal equilibrium and B and C are also in thermal equilibrium, then A and B are in thermal equilibrium with each other. Even though they don't have any direct contact, A and B will be in thermal equilibrium. So I say once more, if A and C are in thermal equilibrium and also B and C are in separate thermal equilibrium, then A and B will also be in thermal equilibrium to each other. That is zeroth law. So you can write the statement and you have to draw that figure and write the example with the system. Okay. So zeroth law of thermodynamics suggests that there should be some physical quantity which should have the same value for the system to be in thermal equilibrium. That physical quantity is temperature. Okay. So to be in thermal equilibrium, there should be a physical quantity which is in common. That physical quantity will be temperature. That is why when all three systems A, B and C, in my previous example, when all three systems are in thermal equilibrium, then their temperature, all of their temperature remains same. So temperature is the quantity which determines whether the system is in thermal equilibrium with the neighboring system. And when the temperature becomes equal, the flow of heat also will stop. Now, thermodynamic state variables. What are thermodynamic state variables? State variable means it is a variable which only depends on the initial stage and the final state. It does not depend on how the body has achieved a state or what is behind that change of state. For example, I am just keeping water and then heating it. After some time the water will start boiling and water is becoming vapor. So initial condition is water, final condition is vapor. So I have to consider initial condition water, temperature 25 degrees Celsius, final condition vapor, temperature 100 degrees Celsius. I only have to consider the initial and the final state. I don't have to consider any of the transition states, any of the paths. or how it achieved that state. Such kind of things are called state variable. So, thermodynamic state variables are macroscopic quantities which determine the thermodynamic equilibrium of a system. Since these macroscopic quantities describe the behavior of the thermodynamic system, it is known as thermodynamic state variables. So, they determine the behavior of the system and they determine the state of the system also. So, thermodynamic state variable. Example, just now I gave water is turning to vapor. Here temperature, we are just measuring the initial temperature 25 degrees Celsius, and when the water becomes vapor we measure the temperature 100 degrees Celsius. So, we are just measuring the initial and final temperature. We are not taking how the body achieved that temperature. So, temperature is a state variable. Similarly, pressure and volume. So, pressure, volume and temperature are called thermodynamic state variables. So, pressure, volume, temperature and also mass and internal energy are thermodynamic state variables. So, we are familiar with pressure, volume and temperature and mass. We are not familiar with internal energy, that we will discuss in detail. So, these are the 5 things which depends only on the initial and the final system. So, they are called state variables. A system not in equilibrium cannot be described by state variables. It means the macroscopic variables are changing with time and they are not constant. So, pressure, volume, temperature, internal energy, all those things are state variables, and if the system is not in equilibrium, cannot be described by the state variables. See, I have given 2 pictures. In the first picture, here there is a partition in the box, this one, and the gas is there. So, the gas is enclosed in the box. Now, I just removed the partition towards that side. So, when the partition is removed, what happens? It leads to the free expansion of the gas. Now, second one, a mixture of gas undergoing an explosive chemical reaction. Explosive chemical reaction. So, during an explosive chemical reaction, this will be forcefully pushed by the energy of this reaction. Here, the gas is not forcefully pushing it, I am just removing it. I am removing it to that side so that the gas can freely expand. In the second figure, due to the explosive chemical reaction, the force of that chemical reaction pushes this piston towards the right and the gas expands. So, in both situations, the gas is not in equilibrium because it is expanding, and when it is expanding there is a change in the pressure. The pressure is decreasing, the volume is increasing. So, the gas is not in equilibrium and cannot be described by the state variables. Okay, so that is the example. Now, thermodynamic state variables are of 2 types, extensive variable and intensive variable. Extensive variable means they are those that depends on the mass of the system or the number of particles of the system. Mass and number of particles. That means it actually depends on the size of the system. Extensive. That is why I told mass and number of particles. Example, volume, mass, internal energy. They come under extensive variables. Okay. Now comes the intensive variable. So, what is intensive variable? They don't depend on the size of the system. They do not depend on the size of the system. Example, pressure and temperature. So pressure and temperature, remember the examples, okay? Pressure and temperature are intensive variable, whereas volume, mass and internal energy are extensive variables. So these 5 are state variables, remember, these 5 are state variables. Out of that, these 3 are extensive variables and these 2 are intensive variables. Now, equation of state. It shows the relation between the pressure, mass, volume and density. We already know the ideal gas equation. For n moles of an ideal gas, we can write the equation of state as PV is equal to mu RT. PV is equal to mu RT, where P for pressure, V for volume and mu is number of moles. Instead of mu, you can write small letter n also. Small letter n is also number of moles. And R is called universal gas constant, T is the temperature. So for a fixed amount of gas, we can have 2 independent variables, either volume and temperature or volume and pressure. Okay, for a fixed amount of gas, we can have 2 independent variables, either volume and temperature, or you can say volume and pressure. Okay, so that's all in this section. In the next section, we can deal with the internal energy in detail. Okay, thank you.